Hi everyone, welcome to this video. I'm going to go over the design of waveguides, microstrip lines, and coax cables on HFSS. So let's get started. So you can start HFSS by clicking on ANSYS Electronics Desktop, which you should see on all VLSI computers, or if you remote desktop into the server. So first thing we're going to do is to make sure that the project is in the right folder that we want. So if you go under Options, Tools Options, General Options, under Directories, you can change that to somewhere on the H drive. And you always want to put your things on the H drive to make sure that you can access it later. So create a new folder here, call it Demo. So this will be where the project will be saved. And I also want to make sure that I'm using the GPU to make my simulations faster. So under Options, make sure that your GPU is enabled and the HPC license is set to pool. All right, so rename the project to something meaningful. So here I'm going to say video demo and create a new HFSS design. And here I'm going to show you guys the waveguide, so I'll just call that waveguide demo. So for a waveguide, you want to create a rectangular box. So if you click on draw box, you can put a box here somewhere. Under create box, you can define the starting position and the dimensions. So I'm going to start it at say waveguide L over 2 minus and 0 0. And waveguide length, we can set it at 5 centimeters. For the X size, so this would be the length, so I can call that waveguide L. The Y size will be your A dimension, and for that I can set that to 15 millimeters. And Z will be B, and that I can set to 7 millimeters. And if you click on Control D, you can see your full waveguide design. So as you guys remember, on HFSS, if you don't specify the boundaries, HFSS will assume their PEC. And in this case, this is good because we're designing a waveguide that has metallic boundaries. So we'll leave that as that. The next step is to define the waveport. So if you click on F, you can select faces. So we want this side to be a waveport. So if you right-click, assign excitation, waveport, you can leave that. You can name it anything you want. I'll leave that as 1. And here we're just exciting one mode, so it'll be the fundamental mode. And under these options, we can not renormalize. We can renormalize to a certain impedance. For all the simulations that you run, you always want to leave it as don't renormalize. The reason being is that the waveport, we wanted the waveport to take the impedance of the transmission line that it's connected to. If you renormalize, then you fix the impedance, which might be useful in some cases, but for now, we'll leave it as don't renormalize so we can check the port impedance later. De-embedding is another option that I'll show you guys later on. If you want to measure the characteristics at a certain distance away from the waveport, you can de-embed the waveport, but for now, we're not going to de-embed. And if you go under excitations here, you can see that this one, this side became a waveport. Then we can rotate to the other side, so we can define that as a waveport as well. So if you click F, you can select it, and you can assign that as a waveport. And we're not going to renormalize. All right, so we've defined the excitations. Our boundaries are already set because they're going to be perfect electric conductors. Next step is to set the analysis, the mesh frequency, and the convergence criteria. So for this waveguide, I want to run it up to 20 gigahertz. So for the mesh frequency, I want it to be 20 or higher. I can set that to 20. Maximum number of passes, I can set that to 20 passes. You can go for more if you want, but that would mean if the simulation doesn't converge, it would keep going for a long time. Maximum delta S, like I told you guys in the lab, 0.01 is acceptable. And here under options, you want to set the minimum number of passes to 6 and the minimum conversion passes to 3. And so now you've defined the mesh frequency and the convergence criteria. You can also add a frequency sweep. I'll let you guys read more about the different frequency sweeps and the differences between them. But for now, I'm going to run a discrete sweep, say from 1 to 20. For the discrete, you want to run a few points. So I'm going to say a linear step of, let's say, 0.5 gigahertz from 1 to 20. So that's about 39 points. It's exactly 39 points. And I'm going to save the fields so I can plot them later if I want. Okay, so we've defined excitations, our boundaries are set, we've defined the mesh frequency, set the frequency sweeps. Next, we want to make sure that the design is valid. So if you click on validate, you can see that you're good to go, and then you can analyze all. And just wait for it to be done. While it's going, you can play with the color of the box or the transparency. You can make that a bit more transparent. And you can also set the color to something more fun. So you can see here it's solving the 39 frequencies, and because it's discrete, it's running the simulation for every one of those frequencies. That's why discrete takes the longest. All right, so the first thing we want to check is to make sure that design converged. So if you go under results, solution data, you can look at the convergence, and you can see that we've down 6 passes, which is our minimum, and we've converged for all of them actually. So you've converged 5, and the target was only 3. All right, so once that's done, you can plot the S parameters. So you can do a rectangle plot, and here I'm just gonna select all of them. And I'm going to plot for all frequencies that I ran and for sweep, which is the discrete sweep that we've been working with. So you can create a new report. So you can see here there's a cutoff frequency. The reflection is low, which is good, which means it's matched. You can add markers to check your cutoff frequency. So if you have a cutoff frequency that is in steps of, or that's actually like 10.1, you wouldn't be able to see it here, or if it's like 9.9, because we ran a discrete in steps of 0.5. If you want to see a more accurate cutoff frequency, it's best to run a discrete in smaller steps, but that would take long. But instead, you can also run an interpolating sweep with many points to get the exact cutoff frequency for your design. So right now, we only have 10 and 9.5. So if there's anything in between, we wouldn't be able to tell. So if you want more accurate results, you should run an interpolating, or not more accurate, more data points. You should run an interpolating or a fast sweep. Okay, so we're good for now. So we can end the marker mode. You can also plot the S parameters on the Smith chart. So if you go under modal solution data report and click on Smith chart, you can plot S11. And because the design is matched, you will see S11 is in the middle. And it's only matched because the wave port, like I mentioned before, takes the impedance of the line. So the line and the port will have the same impedance, and there will be a match at all times. You can also plot the port impedance by going here and plotting port Z0. So you can see there's a weird behavior around the cutoff, but we usually want to look at the impedance in the propagating region. Okay, so that's it for the waveguide. Actually, I'll show you guys how to plot the fields. So if you select the waveguide box, if you right-click, plot fields, you can plot the E field, the H field, surface current, or the quality factor. But for now, we just want to plot the magnitude of the E field. and we want to plot it at, let's say, 18 gigahertz, so it's somewhere in the propagating region of the waveguide. And if you plot that, you can see the field inside the waveguide. And if you do Control D, that wouldn't do it. And you can also animate the field inside. So if you go under the field overlays, you can right click, animate, and you can see the propagation of the field inside the waveguide. Okay, so that's it for a matched waveguide. Next we can run a simulation for a shorted or open waveguide. I'll show you guys how to do that for an open. So if I copy the design over here, so for an open waveguide, we want the termination to be an open circuit, and the best way to do that in HFSS is to use a perfect magnetic conductor. So I can delete port 2 here, and instead of a wave port, right now if I don't define anything, it will be a PEC, so that would be a short circuit, but instead I can also define a perfect magnetic conductor, so it'll be an open circuit. So again, if you select, if you press on F and select the face, you can assign a boundary that is perfect H. And in order for us to measure the characteristics at the perfect H, we have to de-embed the wave port. So right now the wave port is measuring the characteristics of the waveguide at its own location. But what you can also do is de-embed it. So if you double click and then go post processing, you can de-embed to the length of the waveguide, and that way you can see an arrow. You're measuring the characteristics at the open circuit, which is what we want. Everything else will be the same, so we can just run the simulation. Let's go analyze all. And you can see that once it solves the frequency of the field that we want to plot, it's going to show it. So right now it's already solved 18 gigahertz, which is the frequency that we wanted to look at for the field. And you can also watch the results as they come here. All right, so simulation is done. We can look at the S parameters, and in this case, it's an open, so you can see that in the propagating region, everything is reflected back. And if you look on the Smith chart, so if you see this behavior in the Smith chart, you know that you're plotting frequencies that are in the cutoff region. So when you're plotting the S11, when it's open or short, it's best to just look at the frequencies in the propagating region of the waveguide. So here I'm just going to look from 10 to 20, and if I do that, I can see that the reflection at the open is actually an open. So this side of the Smith chart, if you guys remember, is an open circuit. You can see a nice red dot here. If you do the same thing for a short, you should be able to see the dot on the left side of the Smith chart. Okay, so I would say that's good for the waveguide. So just make sure I save my my project. Next thing we're going to look at is a microstrip line. So if you create another HFSS design, and you can call it microstrip. So for a microstrip line, first we have to put in the substrate, which is going to be a rectangle. And here I'm going to start at minus sub L over 2, 0 and 0. Actually, sub L, I clicked enter too fast. We have to define that as something. So let's say that as 50 millimeters. All right, so let's go back here. The X size will be sub L. Y size will be sub W. These are the variables that I'm defining as I go. And the Z size is just the height of the substrate, so we can just call that sub H. And if I remember correctly, I think that's 1.27 millimeters from the lab manual. Okay, Control D, you can see the whole design. So right now this box is a vacuum box, but we want to define it as FR4. So if I go under Edit, I can search for FR4 epoxy, and I can just say OK. So now this is a substrate material. Next thing we want to do is to put the line on top of the substrate, so I can create a sheet, and I can just put it somewhere for now. And over here we want to start at minus MSW over 2, which is MS stands for microstrip, and 0, and we want it to be on the top of the substrate, so that's actually going to be at a sub H position. And the microstrip line width, if I remember correctly, is 2.43 millimeters. The X size will be the width of the microstrip, so if I just do MSW, and the Y size will be the length of the substrate for now, but I'm going to define it as a variable microstrip L, and set that to the length of the substrate, or actually the width of the substrate, because I took the width as the y dimension. Okay. All right, so that's good. And I'm going to give it a different color so you can see it on top. Give it this color. All right, so you can see the microstrip line on top of the substrate. Well, actually, right now it's not a microstrip line. It's not assigned as anything, but you can assign that as copper or a perfect electric conductor. So if you go under assign boundary, finite conductivity, you can select the material, and I can just look for copper. So right now it's a copper line on top of a substrate. Next thing we want to define is the boundaries. So we want to define the radiation boundary around the line, because that's how the line behaves in real life. There's air around it. So I can create a box, and I want this box to be the same dimensions as the substrate. So we go under sub L over 2, 0, 0. And then this would be sub L. This would be sub W. And for the height, we want it to be more than lambda by 4 on top of the line at the lowest frequency of interest. So our lowest frequency of interest is 1 gigahertz. So so we want to be so at 1 gigahertz, lambda by 4 is 7.5 centimeters. So we want to be at least 7.5 centimeters or more away from the top of the line. So I'm going to say we're sub H because we started at 0 plus 7.5 centimeters. So this creates a nice box around the line, and I'm going to make that box transparent so we can see inside. Okay, so now we have an air box around the line. Right now it's not defined as a radiation boundary, but what we can do is we can select the faces that we want to be radiation. So this would be those 3, and then if we rotate, we can get the other 2. We'll go select that one, and then we'll select that one. So now I selected the 5 faces, and then I can assign them as radiation boundaries. And if you go under your boundaries, you can see that we defined the line as a finite conductivity copper right here, and then we have the 5 faces for the radiation boundary. Okay, the next step is to assign excitation. So that would be with the wave port, and for a microstrip line, the wave port has to be large compared to the line, and it has to touch the line and the ground. So right now the bottom of the substrate is going to be PEC because we did not assign it as any boundary. So we can create the wave port. So to do that, we want to create a sheet in the XZ axis. So I can change the axis here to XZ and create a sheet. Okay, I have to actually go like that. All right, so this sheet will be it will have a width, so we can call it the waveport width over 2. It's gonna start at 0y and 0z. So the waveport width, let's say it's a good rule of thumb is to be more than 6 times 6 or more 6 times the width of the line or more. So I can say 6 times ms width, and over here I'm just gonna say waveport w, and the z size we want it to be again 6 or more times the height of the substrate. So here I'm going to say the height is going to be 6 times sub h. So the waveport has to be as big as you can. This is big enough, but you can also define this whole face as a waveport. But this is okay. So right now we have a rectangle for this side. For the other side, we can copy and paste it. And instead of being at 0y, it will be at the end of the line. So it would be MSL. So right there. So now you have the 2 waveports, or 2 rectangles that we will define as waveports. So let's go ahead and define those as waveports. So a sine excitation waveport. Again, we want to be able to look at the impedance of the line, so we're not going to renormalize, and we're not de-embedding now. So we'll just leave that as is. And we'll define the other one as the second waveport. Okay, so we've done everything now except assigning the mesh frequency and convergence criteria, so we can go ahead and do that. The frequency of interest here, the maximum is 5, so I'll leave that as 5. Maximum number of passes, you can set that to 20, and maximum delta S 0.01. And we'll change those to the same numbers that we had before. And we also want to add a frequency sweep. So I'm going to add a frequency sweep, and this time I can do an interpolating from 1 to, say, 1 to 4, and let's do 401 points. Okay, now check, validate to make sure the design is good, which it is, and analyze all to run the simulation. And we can go ahead and start plotting, even though the simulation is not done. So I can plot the S parameters. So these would only be correct when the simulation is done. So over here you can see S11 or S21 going above 0, and S12 which is not correct because this is a passive structure. And it's done, so you can see the reflection is low, the transmission is high, so it is well matched. You can also look at the Smith chart, just like before, so you can look at S11 and see a nice dot in the middle, which is exactly what we would expect. All right, so this is good for the microstrip line. We can also do a short simulation, so I'm just going to copy and paste that, And now for the wave port, HFSS doesn't like it if you put a short on the radiation boundary. So I'm just going to move that wave port or the end of the line in. I mean, before we do that, let's delete the wave port because we don't want this to be a wave port anymore. So you can just delete that. We want to terminate the line with a short circuit, so we can use this rectangle which we used for the wave port before as the short. So to do that, like I mentioned, HFSS doesn't like the boundaries to be on top of each other, so I can move the line in. And if you guys remember, the line length we can reduce. So now it's set to the same length or the width as a substrate, so we can reduce that. So we can do 70% of that. So now everything has moved in, which is what we wanted. And we can define that rectangle, which is not assigned now, as a PEC. So you right click on it and then assign excitation or assign boundary. We can assign that as a PEC. So right now it's terminated in a short. And in order to again measure the short, we have to de-embed the wave port. So if you double click, and you can de-embed that to the microstrip length. And you can see here the arrow shows that it's going to measure the characteristics at the short circuit. So we can look at those parameters there. All right, so let's do that. So we'll run the simulation. And if you wanted to do that for an open, you would define that rectangle instead of defining it as a PEC. You can define that as a perfect magnetic conductor. Okay, so let's run that. And if you look at the results, we should see a short on this mixture. So we expect something on the left side here. Let's see if we got it. All right, so this is a short. Okay. So microstrip is good. I'll save that. The last design we will look at is the coax cable, and we'll create another HFSS design. So we go under HFSS. We can create. We'll start with creating the cylinders. So I'll start with the outer conductor, and that one from the lab manual was Teflon, so we can change the material to Teflon. And I said outer conductor because this cylinder will be, its outer boundary will be PEC, which is the outer conductor, but it will also be the dielectric that the microstrip line is made of. All right, so we'll start it at 0, and the radius will be half of the outer diameter, and the outer diameter was 3.4 millimeters. The height we can just say coax H, and we can set that to 5 centimeters, and Control D so you can see the whole thing. It's too big. And set that to 2 centimeters. Okay, so outer cylinder is done. Now let's define the inner conductors. So you can create another cylinder. And for that, the material will be copper or a PEC, and it will be the inner diameter for the radius, actually that one, that's what we want. So we'll start that as 0, the origin as well, just like before. It will be the inner diameter over 2, and the inner diameter was 1 millimeter. The height will be the same as the other cylinder, and we can play with the transparency and the color. So now you can see the inner conductor, and I can play with that color as well. Okay, so right now we have the 2 cylinders. One is the inner conductor, one is the outer conductor plus the dielectric. What we have to do in order for this model to be valid is we have to subtract the inner conductor from the outer cylinder, because right now they're intersecting. So if you select both of them, you can go under subtract. Your blank part will be the bigger cylinder, so we should move this. We should move the bigger cylinder there. So your blank part is the bigger cylinder, your tool part is the smaller cylinder that you want to take out. And what you also want to do is you want to clone the tool. So you want to clone the inner conductor, because you don't want to just subtract it, but you also want to keep it. So you want to make sure that you select clone objects before operation. And right now, if you rotate, you can see that if we select Teflon, it would actually be hollow inside, which is good. So if you go there, it's hollow inside. Okay, so the model is done, and as for the boundaries, the outer boundary, so so you say F, so this outer boundary over here of the inner cylinder, right now it's not defined as anything, so it will be PEC. So HFSS will assume by default that it's PEC, which is good. We can just leave it as that. The inner one is copper, which is fine. So the boundaries are done. Next, we want to define the wave ports. So in this case, the wave ports would be these surfaces. So we can right click on that, assign excitation, wave port. We just go next, and the bottom one will also be a wave port. So we can select that, right click, assign excitation, wave port. All right. Next, we define the mesh frequency and convergence. So it's going to be the same as the microstrip, because we're going to put them together later. So you can define that as maximum number of passes 20, maximum delta is 0.01, minimum number of passes is 6, and minimum converge is 3. And we'll also add a sweep. Let's do fast this time. Let's do 1 to 4, and say 401 points. And we can save the fields, no problem. All right, I'll rename that coax demo, and make sure the simulation is good, design is good, validated, and analyze all. And you can just preemptively plot the S parameters. It's not going to show because it's not done, but that's okay. And you can also look at the Smith chart. All right, so it's done. Smith chart is matched, as you would expect, and the design is also matched. All right, so this is the end of this demo. I hope you guys learned it.